This presentation is part 2 of liquid mixtures, which shall deal with critical solution temperature and phenol-water system. Here, you will get to know what CST is, upper CST is, lower CST is, and systems containing these, in addition to systems containing both UCST and LCST. You do know that binary liquid mixtures could be completely miscible, completely immiscible, and partially miscible. Generally, for partially miscible liquids, solubility increases with increase in temperature, and the temperature at which they are completely miscible is termed as the critical solution temperature CST or consolute temperature. Temperature composition diagrams are very useful in the description of binary systems, many of which hold good for two-phase compositions at a variety of temperatures and compositions. The composition of binary mixtures are conveniently depicted using these kind of phase diagrams. A pair of liquids is considered partially miscible if there is a set of compositions over which the liquids will form a two-phase liquid system. For most solutes, the solubility is dependent on temperature. For many binary mixtures of immiscible liquids, miscibility increases with increase in temperature. That's what is shown on the screen. The temperature above which the phases of a system are completely miscible is known as the upper consolute temperature UCST or upper critical solution temperature. The phenol water system exhibits an UCST, and this critical solution temperature can be used for testing the purity of the mixture. So here in this figure depicting the temperature composition diagram for phenol water system has an upper critical solution temperature shown at point H. Below H we have two phases existing, and above point H, which is the upper critical solution temperature for phenol water system, we have only one liquid phase existing. Similarly, the temperature below which the phases of a system are completely miscible is known as the lower critical solution temperature. Triethylamine water liquid system shows a decrease in miscibility with rise in temperature. So this figure is the phase diagram for triethylamine and water system. Below the critical solution temperature, water and triethylamine completely merge with each other, and we have only one phase existing. You can see that in the figure. The bottom of the curve has a point shown as T. LCST, and below this LCST we have only one phase existing. Nicotine water system is a partially miscible binary liquid mixture showing both upper CST and lower CST. You can note that here. Upper CST for the nicotine water system is 210 degrees Celsius, while the lower CST is 61 degrees Celsius. So above 210 degrees Celsius, we have a single phase of nicotine water, and below the lower CST at 61 degrees Celsius, we have a single phase for these two components of the binary mixture. Here you have a figure showing all these three systems. Part A of this figure shows UCST. So above UCST, we have a single phase existing. Part B shows a system with LCST. So below this temperature, we have only one phase existing. Part C shows both UCST and LCST. So above UCST and below LCST, we have only one phase region, and part D of this figure shows a system which has neither LCST nor UCST. We have the example of diethyl ether and water system for a mixture which has neither LCST nor UCST. You have several examples of binary liquid mixtures shown here, which possess only UCST, only LCST, and both UCST and LCST. The compositions of the single phase is also shown in the last column. This is another figure depicting LCST and UCST. Coming to phenol-water system. When phenol and water are mixed, a certain amount of the two dissolves with the other due to hydrogen bonding, and two conjugate layers of liquids are obtained. The upper layer of this system is water dissolved in phenol, and the lower layer is phenol dissolved in water. The composition of these layers depends only on the temperature of the system and is independent of the quantities of the liquids mixed. For every temperature, two solubilities can be obtained, one for phenol dissolved in water and the other for water dissolved in phenol. The variation of mutual solubility of water and phenol with temperature is shown in the temperature composition curve on the screen. Point A is the system containing 100% pure water. That's shown to the left in the figure. Addition of phenol to water will result in the formation of a single liquid phase until point B is reached. At point B appears a second phase. Phase A, water-rich phase containing 11% phenol, and phase B, phenol-rich phase containing 63% phenol. As we increase the quantity of phenol, or as we proceed from point B to C, we get systems in which the amount of the phenol-rich phase continuously increases. At the same time, the amount of the water-rich phase decreases. Once the total concentration of phenol exceeds 63% at 50 degrees Celsius, a single phenol-rich liquid phase is formed. So, at 50 degrees Celsius, we have an aqueous phase saturated with 11% phenol, shown as point B, and a phenolic phase saturated with water containing 63% phenol, shown as point C. The line BC drawn across the region containing the two faces is called a tie line. Tieline. Tie line can be used to determine the composition of the two components in the liquid phase. An inverted parabola curve obtained shows the limits of temperature and concentration within which the two liquid phases, namely phenol and water, exist in equilibrium. The region outside the curve contains system having only one liquid phase. Below the curve, there will be existence of two liquid phases. Amount of phenol-rich phase continuously increases and the amount of water-rich phase continuously decreases when phenol concentration is increased. The maximum temperature at which the two-phase region exists, called the critical solution temperature, is 68.1 if both water and phenol are 100% pure. To phenol water system, if impurities of ionic and covalent substances are added, a ternary system is obtained. For a ternary system, there are three components coexisting in a system. The addition of a third substance to a partially miscible system to increase its miscibility is known as blending. If the added salt dissolves in one of the phases only, it results in an increase in the UCST and a decrease in the LCST, thus decreasing the miscibility of the system. Further, if the added salt is soluble in both the phases, then the UCST is lowered and the LCST is raised, thus increasing the miscibility of the system. This increase or decrease in the CST depends on the nature and the mass of the added substance and the composition of the system. That is it for today. We'll meet in the third session of liquid mixtures.